Okay, in this lesson, I'm going to teach you about the mole. It's kind of an important concept in chemistry. And here we go. Well, the first thing you guys need to be aware of is that a mole is a word that is used to represent an amount of substance. Okay, so it's just a word that represents a number. Okay, so just like if I say a dozen, well, I mean, you guys know that a dozen is 12, right? 12 what? Well, I don't care. 12 pencils, 12 eggs, 12 school buses, 12 shoes. It's a dozen. A dozen is 12. Doesn't matter what, it's just a quantity. Same thing, a pair, okay? If I'm playing cards and I've got a pair of jacks, I've got two. I've got a pair of shoes, I got two shoes. Got a pair of pants. That's only one. Well, maybe it's the two legs. Yeah, that doesn't work though either because then you'd have a pair of shirt because it's got two arms. I don't know. Pairs two. Okay, a gross. I don't know if you guys know what a gross is. A gross is a dozen, or 144. A mole is just like all this stuff. It's a number. 6.02 times 10 to the 23rd power. I don't care what you're talking about. It could be pencils or school buses, stars in the sky, whatever. I mean, it's a quantity, it's a number. Okay? Just so you guys are aware. This number is huge. That number's big. That is a giant number. Okay, just to give you some idea. That's what that number looks like, right up here at the top. If you were to write it in standard form, it's basically 6 followed by 23 zeros. If you were to say that, you would say 602 sextillion. That is a really big number. Just to give you an idea how big that number is. If you had a mole of grapefruit, that grapefruit would occupy the volume of a solid sphere. It'd be planet grapefruit. It'd be the size of the Earth. That's big. And not just a hollow shell. I mean, just like grapefruit on top of grapefruit piled, like a solid core of grapefruit, size of the Earth. It's a lot of grapefruit. If you had a mole of sheets of paper, you could make 1,000,000. Oops, I forgot a zero there. There should be a zero. Let me add it. There. You could have 1,000,000 equal stacks from the Earth that would reach to the sun. The sun's 93 million miles away. Paper's pretty thin. That number's big. Okay, let's say if you could see every cell in every living person on Earth, and there's about 7 billion people, there's just about a mole of human cells in existence. And the thing is, you can't see any of them. Well, there's only one. There's one cell in the human body you can see with the unaided eye, and that's actually in females, their egg. Okay, so like in the reproductive organs of females, their eggs, they're about the size of a period on a printed page of, just regular 12-point font. The period at the end of the sentence, that's how big the human egg is. Everything else, invisible, too small to see. So every person that exists right now, if you could get them together and you could see all their cells and you could count them, there is about 1 mole of them. That is insane. Just to put this in perspective, let's say that you were a millionaire. Okay, you had 6.02 times 10 to the 23rd dollars. And let's say that you had the ability to spend $1 billion per second, every second of the day. How long would it take you to run out of money? All right. So, people think, man, 1 billion, that's pretty quick. It shouldn't take very long for you to run out of cash. Well, fortunately, guess what? We don't have to guess or think about it. We can use our friend dimensional analysis to solve this. Okay, so what I would do, let's see, I'd probably set this up like so. Okay, so I'd say dollars over here. Let's start with our mole of dollars. 6.02 times 10 to the 23rd dollars. And let's convert that time into money. Or money into time, I guess, the other way. Reverse it. Yeah, time is money, friend. Okay, let's see. Let's put, we said we could spend $1 billion per second. So we need to get rid of dollars. They need to go on the bottom. How many? Let's put a billion down here. So 1 times 10 to the ninth dollars. And we're going to say, let's make certain that looks like a superscript. 1 times 10 to the ninth dollars, and let's say every second. Okay, dollars are going to go away. Time is now the unit that's left. So money has become time. Okay, well, I hate to be the bearer of bad tidings, but seconds isn't going to be real meaningful. All right, so we're going to have to convert this in, and honestly, the answer is going to be in years. So let's continue. Let's see, seconds. I can say there's 60 seconds in 1 minute. Seconds go away. I know there are 60 minutes in 1 hour. Minutes go away. There are 24 hours in 1 day. Hours go away. I have days. There are 365. Let's put 0.25 for those leap years in there. Days in 1 year. So if you take this to solve, you're going to take 6.02 times 10 to the 23rd divided by 1 EE9 divided by 60 divided by 60 divided by 24 divided by 365.25. And what you guys are going to find out if you could spend $1 billion a second, every second of every day, 24 hours a day, 7 days a week, 365 days a year, it'd take you about 19 million years to run out of dollars. That number is unfathomably huge. You can't conceptualize it. It's so big, it doesn't have meaning. It's giant. And you know what the important thing is? Maybe if you want to take anything from this, guess what? And dollars and things are nice, but you know what? These guys are the limiting things. So in your pursuit, in your life for money and for things, material things, look around, realize that those things that you own, they were once money. And that money you traded for time of your life. So your things are replaced by time in your life. So keep that in perspective. Granted, you need things, but you need to establish a balance. Okay, let's go on to the next deal here. So let's say we could count up every water molecule on Earth, every drop of water in every ocean, lake, river, stream, glacier, aquifer, dasani, bottle of water, toilet bowl, blade of grass, dead cat. How many moles of water molecules do you think there are? And as you're sitting there thinking, some people think, oh, there's, 1 mole, maybe there's a fraction of a mole, maybe there's, a few moles. Some people even say maybe there's a mole of moles. Well, I hate to be the bearer of bad tidings, but I don't know the answer. I don't know how many moles of water molecules are on the Earth, but I can show you this. This is 1 mole of water molecules. Okay? Not very much. If you look at it, that's about 18 milliliters. 18 milliliters of water is 1 mole of water molecules. What does that tell you about water molecules? Holy schmoly. They are tiny. Molecules are small. Okay? If you can fit 602 sextillion of them in this, that means they are tiny. Okay? So, moles then are used to quantify things that are extremely tiny, like atoms or molecules. Anything that's large enough to see, it's far too large to be quantified by the mole and take up just too much space. So the only thing you'll ever really see moles attached to is like atoms, molecules. You can measure subatomic particles like electrons with it, but that's about it. Anything else, far too big. Now you might say, how did I know that was a billion? Or excuse me, not a billion. How did I know that was 602 sextillion water molecules in that graduated cylinder? Even if I could count them a billion at a time, I could go like 1 billion, 2 billion, 3 billion. 4 billion, 5 billion. It'd take me 19 million years to count them. I don't have that kind of time. So what you guys need to be aware of is that we can use this counting by weighing thing. Okay, so 1 mole of any element, it's equal to that element's atomic mass based in the unit of grams. So this is where we're going to need our periodic tables back. So hopefully you guys have them with you. If not, I'll give you a digital copy. I'll put on the classroom. But yeah, you need to know the atomic masses. They become super important to us. Okay, so if you get out your periodic table, and you look at these, so you look at carbon, you find its atomic mass. It says 12.01, and so 1 mole of carbon weighs, you're going to say 12.01 grams is for every 1 mole. Okay, nitrogen has a different atomic mass. You look at nitrogen, 14.01 grams. Oxygen has a mass of, my pen's crapping out here, 16 grams. You look up sodium, 22.99 grams. So all of these elements have different atomic masses. So if I want to find the atomic mass of a compound, all I have to do is sum up the masses of the component elements. So I know water's formula is H2O. That means I have 2 hydrogens, each weighing 1.01 grams. I have an oxygen that weighs 16 grams. So 2 times 1.01 is 2.02 plus 16, 18.02 grams per mole. And that's the appropriate unit for molar mass, grams per mole. You will also notice that MOL is the abbreviation for mole. Okay. And, you're like, well, that sucks. That's not a very good abbreviation. You only get rid of 1 letter. Well, it is what it is. But that is how you calculate molar mass. All you do is add up the components. That's it. Pretty easy. Let's do a couple more. Let's say I want to do a mole of sodium hydroxide. So I need to know how to write the formula. Hopefully you guys haven't forgotten how to do that. That's going to come back and bite you in the butt. Sodium hydroxide. So we have sodium weighs 22.99. Oxygen has a molar mass of 16. Hydrogen is 1.01. When you sum those all up, 40.00 grams per mole. That is the molar mass of sodium hydroxide. Sodium chloride, same thing. So you need to write sodium and chlorine. Sodium is 22.99. Chlorine is 35.45. If I sum those up, should be 58.44 grams per mole. Easy stuff. One more and we'll call it good. Okay, let's say I have a mole of calcium acetate. So you have to remember calcium is 2 plus, acetate is C2H3O2, it's 1 minus. So when you write the formula, it has to be in parentheses, and there's a 2 there. So let's see, calcium weighs 40.08. We multiply this, so there's a total of 4 carbons, each weighing 12.01. Multiply here, so 2 times 3, you have 6 hydrogens, each weighing 1.01. And then oxygens, you have 4, each weighing 16. Okay, so what you're going to do is multiply, and then sum all of them. When you do that, you should get 158.18 grams per mole. Just so you guys notice, for sig figs on this stuff, whenever I'm doing molar masses, I always use 2 decimal places. And the reason why I use 2 decimal places, that's what our balance is. If we were in the classroom, you notice they all go to 2 decimal places. So that's as accurately as we can measure in the classroom. So that's why whenever I do molar mass, I always just do 2 decimals. These really don't count for sig figs because these are taken from a table of elements, so a value of constants that everybody uses, so they're not really measurements. So that's why when I write them, 2 decimals. Okay, so I'm going to give you guys a worksheet, and you guys can practice some of these, and that'll be it for the weekend. All right, have a good one.